Hello everyone. In this lesson we are going to talk about bending. Here you see a beam, simply supported beam. Here it is pin supported, the other end is roller supported. You see picture of the earth as well. It is just to represent gravity. I cannot show the gravity here, but I can represent it by a magnetic field. Sorry. As I apply a gravitation-like force, gravitation and magnetic force are similar in sense that they can pull without contact. So the magnetic force is like gravity, it is pulling without any physical contact. Here I can show that the magnets, like gravity does, pulling the beam. So the gravity, as you know, pulls everything down to the center of the earth. We apply the gravity and the beam bends. So this is also called sagging. So the sagging is what happens all the time on earth on the shafts and beams due to their own weight. We may not see it by naked eye, but this sagging definitely occurs even in very small scales. So this is like a distributed load. The beam has got a mass. There is also a pulling force, which is gravity. When we multiply mass by the gravitational acceleration g, we obtain the weight, and this weight is like a distributed load. Is actually a distributed load on the beam. So if we draw this beam here, our topic is bending. Let's write it here. We have got a distributed load, which is the weight of the beam itself. We show it with W. Due to the gravity, this beam sags like this. Actually, not only due to the gravity, but also due to the mass. We need both of it for the deformation to occur. So let's give length as well. It has also got length, and name here as A, this point B. And our coordinate system, now we are working on 2 dimensions, so we have got only x and y. These are the reference positives. In this case, in such a loading condition, the beam has got internal loads all across the body. We choose any point and get a section there, we will definitely see a type of internal load. At some points it can be 0, but we will definitely see all across the beam either shear force or bending moment. Bending moment is actually the couple of the normal loads, and we can say that due to bending, any of the section would have two components of the load. If we draw it here, say that I cut the beam here, so this section. By cutting we get two segments, segment 1, segment 2. I draw segment 1 here, segment 1. When I look at this face where the cutting occurred, this face of the segment, I see two types of loading, two components of internal loads. One is shear loads, and the other is normal loads. It is called normal because it is normal, orthogonal, and vertical to the surface. This is parallel to the surface. Normal forces are, or normal loads are vertical to the surface, and the distribution of the normal loads would be like this. Here there will be compression, and at the bottom half there will be tensile. Compressive normal loads and tensile normal loads. How do we know that there is compression at the top and there is tension at the bottom? Due to the sagging like this, so that sagging happened, you see that if we exaggerate it, so we can show it by a point load. I apply point load. You see that top portion, if we draw a line here, this line gets shorter, and if we draw a line at the bottom of the beam, we would see that this curve, this line would get longer. So the top surface is getting shorter, the bottom surface is getting longer. So what makes it shorter is a compressive force, and what makes something longer is the tensile force. Therefore the top part is normal, bottom part is compressive normal load, bottom part is tensile normal load. At the mids, if you draw a line at the mid of the beam, you wouldn't see any change in its length. Therefore the normal load is 0 at the midsection. It's also called neutral axis. So if you draw an axis here, this is called neutral axis. We will talk about it later. So the resultant of these forces, if you want to get the resultant of shear loads, it is called average shear force or average shear load. And the resultant of the normal loads here, in terms of load, it is actually zero, because the magnitudes of the compressive and tensile forces are equal to each other, but their directions are opposite. Therefore, they make them they cancel out each other. But these two sets of forces, the compressive and tensile forces, creates a moment. So there's shear here, downward, and moment here. The moment caused by normal loads, or can be substituted by moment. It is vice versa. So the moment here is counterclockwise direction. Shear force here is downward in negative direction. But when it comes to drawing shear moment diagrams, these are the positive directions. This is assumed positive direction for shear force. This is assumed positive direction for moment. Okay, let's carry on this segment. If I draw a free body diagram of the segment 1, don't forget that beam analysis, the beam bending analysis of the beams, are done on the left hand segment. So on the surface, on the right surface of the left hand segment, the shear and moment for the values we see on the shear moment diagrams, they belong to the right hand surface of the left hand segment. Left hand segment, right hand surface of the left hand segment. Okay, we draw a free body diagram of the segment 1 in 2D. These were in 3D. And this is in 2D. Free body diagram of segment 1. Here we have got distributed load. Just remember that this distributed load is the weight of the segment. Here it was, what you see as a distributed load is the weight of the whole beam, but here it is the weight of this segment only. And we have got reaction forces RAY, RAX. At the meantime, we should be aware that RAX is 0. Why? Since there is no acting force horizontally, there is no reaction force horizontally. Action, reaction, no acting force horizontally, no acting force, no reaction force horizontally. Therefore, RAX is equal to 0. So these two are the external forces we have got, RAY and W. And by the way, we need the length of this segment. Let's call it x1. In order to keep the segment 1 in equilibrium, there are internal loadings here. One is, as we said here, one is shear force, the other is moment. So if we want to give directions for this, it is downward, as I told here, it is downward here for the shear force, and it is counterclockwise direction for the moment. These are the positive sign conventions for shear moment diagrams. So if your shear force is downward, you draw it in the positive area of the shear diagram. If your moment is counterclockwise direction, you draw the moment graphic, in positive area of the moment diagram. Okay, and let's find what V is. So this was x1. We want to find V, the unknown. So by the way, RAY is equal to W times L over 2. So this is equal to W times L over 2, because the distributed load is shared equally by the vertical reactions at A and B. Therefore RAY is W times L over 2. If I write the vertical force equilibrium equation, W times L over 2 minus W times x1 and minus V. If I solve this, V is equal to V is equal to W over 2 times, this is L, not 1, L minus x1. We know that x1 is much smaller than L, therefore the result is positive. You see that the result is positive, and this is the case for such a simple, for the most fundamental example of the bending. Therefore, this direction is assumed as positive in shear moment diagrams. So let's do it for the moment as well. Let's find what moment is. So I take moment with respect to this point. So the moment caused by RAY is W times L over 2. Which is minus because it is trying to rotate this segment around this point at clockwise direction. Therefore it is minus W times L over 2. The moment arm, the force arm is x1. W is causing, we can show the resultant of W. Resultant of W is this, W times x1. It is trying to rotate the body, the segment, in counterclockwise direction. Therefore it is positive. W times x1 times the force arm is x1 over 2. And finally, on this point, around this point, the third term that is acting, the third moment effect is the internal moment, and it is shown in positive direction. If we calculate this, we can take the W x1 over 2 parenthesis and L minus x1. Again, just remember L is larger, much larger than x1, therefore this result is positive. So the directions we show here are the true directions, and this is the case in initial parts of this segment. So for such a fundamental beam problem, I can say that it is the most fundamental beam problem because there is no external additional load. I mean, of course, the distributed load due to its own weight is a external load, but there is no additional force. The beam is sagging due to its own weight, and the boundary conditions, the supports, are also basic. The boundary conditions are the basic, and the loading is basic. Therefore, the bending problem, such a bending problem, can be called as a most fundamental bending phenomena. Therefore, in such a case, in such a fundamental situation, the result is this: V is showing downward, moment is showing counterclockwise directions, and for such a fundamental situation, these results, these internal force directions, loading directions, are assumed as positive. Okay, this is positive, this is positive. Okay, what else for this part of the lesson? Okay, in the next lesson we will continue on the shear moment diagrams in more detail. Thank you for listening.